Hi, my name is Aaron Jerome. This is my second electronics video. Welcome to my second electronics video. I am, you can see this, of course, hopefully you're seeing this on my YouTube channel, Jerome Electronics, spelled with an X at the end instead of an ICS. My email, in case you want to contact me, is jeromeelectronics@gmail.com. I teach electronics, an objective approach to artificial intelligence that can be used to drive automation and robotics. I believe that student interaction and animation are critical to helping students to quickly understand and retain new knowledge. My methods might be a little bit unorthodox at times, but if they are incorrect, I am not afraid of making mistakes. It's how I learn. It's how I improve. Please help me to improve my presentations before or by offering corrections. I really do appreciate your input, and it helps everyone. So this is my second presentation ever. I try to have student worksheets available. This is not as big as a worksheet as last time. It's basically a table at the top, what we call a circle T, which I will explain, and then a space for things like schematic symbols, specifically the resistor and the variable resistor schematic symbols that we're going to be using. In any case, I do appreciate your input and helps. This picture is just about a bunch of components because I'm just introducing components. We will introduce in this video resistors and capacitors specifically. We'll talk more about what capacitors are in more detail later on, but I'm going to talk about how to read them because reading capacitors is so similar to how you read a resistor. Okay, so what is a resistor? Well, water and electricity are really similar in nature, so we compare them all the time. The drops of water are compared to electrons, and they both flow. Both electrons, if they flow, or drops of water, if they flow, are called current. So what happens to the banks of a river when the current is too strong? In this case, as you can see, it starts to blow out the banks of the river. It washes out the bank. This is very similar to what happens when a current of electrons is too strong. It begins to blow out its banks too. With electrons and wires, well, what happens there is the wire melts and the break is known as an open, and it used to be in the old days when the wire would melt, it would melt over the pile of newspapers on the back porch and start a big fire. Well, that's why somebody invented fuses, which we will talk about a little bit later. In any case, consider that too much water is not good, and too much flow of electrons, too much intensity is not good. So with water, what people do is they found that by putting obstacles in the path of the water, they can slow down the intensity of the current so the damage can be prevented. These guys are putting bales of straw in a place where water will drain off a mountainside, maybe the water when the snow melts. It'll hit these bales of straw and slow it down, and then there will be less erosion of the banks of the stream. On the right, you're seeing the same thing, only these are bags of straw that are staked down. They might be bags of sand, but they are slowing down the flow of the current, or they're reducing the intensity of the current so things don't blow out. An electrical circuit needs work to do. If it doesn't have work to do, it gets into trouble. So everything, quite often, is called a resistor because if you connect power directly to ground, that's always bad. So resistors are basically gadgets that can simulate work, but really a light bulb, a toaster, whatever you've got that is the work that is done is the resistance generally in a circuit. Well, we're going to talk specifically now about resistors. So, resistors are used all the time in electronic circuits. A resistor is an electronic component that resists the flow of electrical current, and it's typically used to control the amount of current flowing in a circuit. Resistance is measured in units of ohms. The reason it's measured in units of ohms is because of this guy. His name is George Ohm. And the symbol for it is a Greek letter omega, which is so similar to ohm. And since resistance was named after George Ohm, it was just natural to use the omega symbol to represent ohms of resistance. Why did we name it after George Ohm? Well, he was the first guy to really understand, as far as we know, the relationship between voltage and current and resistance. This little thing here, this little circle with a T in it, we call that a circle T. It's been used for over 100 years in electronics. What you'll find in the books is a triangle with a T in it. Doesn't matter. But I should point out what it is and what it means. The circle just kind of holds everything together in one cohesive idea. And the horizontal line in the middle is a per line, which is the line you would use when you would divide. So the things above the per line are divided by the things below the per line. And so basically, E is divided by I times R. Why I times R? Well, the vertical line in the bottom half means multiply, or it's the byline, as in 2 by 2, 4 by 4, 2 by 4, things like that. It always means multiply. So basically what we're doing is using this. We'll talk more about this later on, but it basically talks about the relationships between voltage, current, and resistance. Now, before this point, people generally knew what voltage was. They generally knew what current was. But what George Ohm did was he told us there is a relationship between them that is moderated, I guess, by resistance. So basically, the idea here is if you don't know the current, but you do know the voltage and the resistance, you can find the current by dividing the voltage by the resistance. Think about maybe covering up the one you don't know. If I don't know what the resistance is, I can take the voltage and divide it by the current, and that will give me the resistance. That's the relationship that George Ohm figured out, understood. If you don't know what the voltage is, and you do know the current and you do know the resistance, you simply multiply the current times the resistance, and that will give you the voltage. Now, the circle T on the worksheet that goes along with this is meant for you to put this information there to help you remember the relationship that we call Ohm's law. I think I talked about this in my last video, but if not, I'll talk about it now. E is really the true name of voltage. There is a problem where electricians, electrical engineers use bad grammar. For example, if I were to say, what is the length of a stapler? You would use that. You would use a ruler of some kind to figure out the length, and you would perhaps use a ruler that has inches, and then you could tell how many inches it is. The question is, what is the length? The answer is given in inches. In that example, the question here should be, what is the electromotive pressure, which starts with an E? And the answer would be voltage. Well, I guess we're lazy. So we say voltage in the question and voltage in the answer, but sometimes you see the letter E pop up, and that means voltage, but it stands for electromotive pressure. So electromotive pressure, voltage are the same thing. We will talk more about that later as well. I is for current. Sometimes you'll see an A here for amps, an I for intensity, sometimes a C for current. They are pretty much describing the same thing as well. Resistance, you'll see an R. You might see the word ohms in this quadrant, or you might see the omega symbol there. And that's the relationship that George Ohm figured out. At the top of the page, you're seeing the official schematic symbol for a resistor. It is a line that is squiggly, and then there's a true resistor over here. We remember this line to me looks a little bit like Charlie Brown's shirt. So that's how we know, I guess, that Charlie Brown was a member of the Resistance. And we should all join the Resistance. We could join together now and say, Om. Of course, I'm just joking. Moving on. There are several different kinds of resistors, types, and package styles that we need to know about. The most common is carbon film resistors, and they're the ones that have the color bands on them. Generally, you see 4 bands on these things. We're going to talk later in this presentation about what those bands mean. Another kind of resistor, carbon film, is a type that has 5 color bands on them. We're not going to mess with those. They are just... I don't know, there's more information, don't want to mess with it. It isn't relevant to what we'll be doing. There are surface mount resistors. Basically what these things are is these are resistors that robots can use to automatically place the resistors rather than having a person place these resistors. So these are surface mount. The robot would set them down, they'd be soldered in place. I suppose robots could do the other kind too. These are old pictures. These are really, well, they can be much smaller than this. I'll show size comparisons in a minute. But there's another kind of a resistor, and that is called the variable resistor. Variable resistor means that you can actually turn a knob and increase or decrease the resistor. This class, this topic, this subject gets a lot of pushback for being a class that reminds people of shady cultures. And this is the first reason why. Variable resistors have another name. It's potentiometer. Of course, that's a long name. Both of those names are long names. So people in electronics world, they call them pots. So this is not a pot course. You go somewhere else for that. But that is what they call them, and it's not my fault, but it's just what they're called. Here are some size comparisons of the different resistors I've shown you compared to a dime. Some are big, some are small. Now, what if we wanted to know how much, I mean, just like water in a stream, you put a straw bale there and it reduces the intensity. We want to know how much each of these resistors reduces intensity of the electrical current that's going through them. And that's what those color bands are about. But those are not the only way to figure out what the resistance is of the resistor. I can think of 4 ways just thinking about it. Probably the easiest way is to use a multimeter. Another way is to use Ohm's law. We just talked about it. You can find resistance by using Ohm's law. Another way is to figure out the color code. Now, I said 4 different ways. I'm going to talk about another way a little bit later, and that will be Kirchhoff's laws. Kirchhoff's laws are another way for us to be able to figure out resistances. And so that's the 4 different ways. A multimeter, color bands, Kirchhoff's laws, and Ohm's law. Those are the 4 different ways. Okay, now I'm going to take a turn for the worse. I'm going to show you this image, or this video. This is a yodeling goat. Why am I showing you a yodeling goat? Well, it lends legitimacy to the next thing I'm going to show you, yodeling goats. I'm going to now tell you the story of Violet and her yodeling goat. This is relevant and important, and you need to memorize the entire story. So you want to record it. You'll want to record it on your worksheet. In my class, I have my students record it into their workbooks, into their logbooks, their engineering logbooks. We keep those. And so here goes the story. First, we're going to talk about it in great detail, so don't try to memorize it with the first time through. Don't even try to write it down. Just pay attention to what's going on my screen. Here is the story of Violet's yodeling goat. Bully Brown ran over a yodeling goat because Violet's granny was gone snorkeling. The end. It's the end. In any case, I'm going to state that story one more time, which means I'm going to jump back. Just restating it. Don't bother writing it down yet. We will write it down in just a second. Bully Brown, notice the first letters are a different color, ran over a yodeling goat because Violet's granny was gone snorkeling. The end. Okay. What does that all mean? Well, you're going to take your worksheet and you're going to write down the story. So let's do that now. Bully, write it down. Brown, ran. I want you to put over A in the same column. A is actually not used, but we need a place to put it, so we're going to put it there with over A. Yodeling, goat. Do you remember the next part? Because Violet's granny was gone. Remember the last part? Snorkeling. Okay. So, those of you who've been paying really close attention and are Jedi Masters probably have already figured out what I am trying to say here. What is the secret code to the story? Well, the secret code of this story has to do with the first letter of each word. And if you look at it closer, some students look at this and they say, oh, I can see Roy G. Biv in there, which are basically the colors of the rainbow. I can see brown, I can see violet. And if you think about it for a second, you realize each one of these words represents a color. For example, the first one is going to represent black. So you'll want to write that down as well. You don't have to color it in, just write down the word black. The second word, if you think long and hard about it, you realize that that is brown. And incidentally, there are three words that start with the letter B over there. If you look over about in the middle there, you'll see the word because. And the word because is also a color that starts with the letter B, and it's in the rainbow. It's probably a good thing that black and brown are not in the rainbow, but because, think about it, we'll get there in just a minute. R, what does R stand for? Well, it starts with the letter R, red. Over, what color starts with an O? Hopefully, and let me stop and point this out. You're actually learning better if you're trying to answer the questions before I actually tell you what the answers are. This is through the entire class. Try to work ahead of me. If you get it wrong, if you've been trying to work ahead of me and you get it wrong, what does that mean? That means you found a correction. That means you learned something. If you learn something, in my mind, you created another brain cell. If you're increasing your brain power, your brain cells, your knowledge, you're evolving. You're becoming more mature as an individual. So, work ahead of me. Of course, the next color is going to be orange. Yodeling, that starts with a Y. The color that starts with a Y is yellow. Goat. Goat, well, that starts with the letter G, but there are also two other words that begin with the letter G. Goat, which is a color, by the way. It's going to be in the rainbow because we've got Roy, red, orange, yellow. That's Roy, G. That's, and then Biv, B. Indigo is not in this group, but in physics, it is. So violet is the last color in the rainbow, so you got Roy G. Biv. What I'm getting at is this goat, this G, it has to be the color green because the other colors that start with the letter G are not in the rainbow. Although gold is at the end of the rainbow. But we'll talk about that in a minute. Okay, the other B, we talked about it before. Hopefully you guessed that it was blue. Violet, that is the color violet. Granny, what color is her hair? It's gray. Granny is gray. That's how you memorize this color. Was. was. What color starts with the letter W? Well, technically, I guess in some instances you would call it every color, and in other instances it would be called no color. It's the color white. Okay, I told you there was a color, gold is at the end of the rainbow. Well, that's G for gold, and that is the third G color, green, gray, and gold. The last one, snorkeling, that stands for the color silver. Now, these colors, they all have a number associated with them. And the number associated with each one of these colors, well, it's pretty simple. They just go in order. Just make sure the color black represents the number 0. Start with 0, not 1. We do that a lot in this topic, in this class, in this course. Start with the number 0 and then just start counting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 0 through 9 there. 0 is black, 1 is brown, 2 is red, 3 is orange, 4 is yellow, 5 is green, blue is 6, 7 is violet, 8 is gray, 9 is white. Well, we've pretty much run out of symbols here, but write down that gold represents 0.05 or 5%. Silver is 0.10 or 10%. Okay? Now, with this table, the reason this table is so valuable is that it helps us to look at a resistor and figure out the amount of resistance that that resistor might provide. For example, we're going to be using the color bands now. This has always been a problem with resistors. People look at the color bands and they're either colorblind or they're hard to see or something, which is why it's nice to have 3 other ways to figure this out. But if all you've got is the color bands, we can actually figure out the resistance of this resistor, the resistance that this resistor provides on those 3 color bands. So to help you out, I'm just going to say this one is yellow, this one is violet, and this one is red, and this one is gold. Now, to figure out the amount of resistance in this resistor, all we need to do is take the color band for yellow, look at a chart up above, and it says, well, yellow is 4. So we put a 4 right there, and we've got the first color band of this resistor decoded. The second color is violet. That's the second color band is violet. That is a 7, so we're going to put a 7 down there. The third band is a red, so we could put a 2 down there because red is 2, except things change right here. That's why I've made the 2 actually red. Things are different here. This third band is called the multiplier band. And the multiplier band tells how many zeros to attach to the number, so we could just say 2 means put 2 zeros here. Or technically, the multiplier band tells us how far the decimal is moved to the right. So if the decimal was just to the right of the 7 and we moved it 2 more times, we'd have 2 spaces and we would fill those with zeros, which means it's basically just how many zeros we tack onto this number. Now, even more technically, it is how many times the number is multiplied by 10. So 47 times 10 is 470. Multiply it by 10 again, you get 4,700, which is the same thing as putting 2 zeros on the end or moving the decimal 2 places to the right. So that's basically all saying the same thing. So this, technically, is a 4,700 ohm resistor. It provides 4,700 ohms of resistance to an electrical circuit. Well, this resistor slows the flow of electrons with a resistance of around 4,700 ohms. Why did I say around instead of exactly? Well, there's more to the story, and it involves that gold band over there. Resistors provide a range of resistance, not an exact resistance, but we need to be able to name our resistors, so we name them with the middle resistance of the range. So even though we call this a 4,700 ohm resistor, The range is told by the last or the metallic band. The metallic band should be on the right side when you read it. It's going to be gold, probably in most cases, because that is a more precise indication. That is a more precise application of a resistor. Okay, so the gold band. So what we do to figure out the full range of resistance of this resistor is we take that 0.05 that is associated with the color gold, and we're going to multiply the 4,700 ohms of resistance by that 0.05. We could also multiply it by 5% and we'd get the same number, but we multiply it by 0.05. We get from that 235. We're going to take that 235 and we're going to add it to the result. So 4,700 plus 235 is 4,935. This happens to be the upper limit of the resistance range that we're talking about. So there it is. That's how you figure the upper. But to figure, that's the maximum. To figure the lower end, you would simply do the same thing, only this time you would subtract that number from the 4,700. That would give you 4,465. That would be at the minimum end of that range. And so now we know that this resistor, this particular resistor, serves any resistance within that range. So if you're making a circuit, it'll serve any resistance within the range. So we call that middle number the nominal resistance. Nominal is another word for just named. So that is the named resistance of this resistor. But there is a range. Now, I want to stop here and mention that there is another band, kind of, that would be in the place of the gold band or the silver band. The reason I say kind of is because it's a transparent band. In other words, if it's not gold and if it's not silver and there's no band there and it looks like there's only 3 on this resistor, what that means is it's the transparent band at the end, and that is actually a 0.20 or 20%. We don't see those very often. We don't use them very often. I think I might have one in one of my tests somewhere, but we don't really worry about that. I just wanted to mention it in passing. So the name of this resistor, its nominal value is its name, is 4,700 ohms. That's the named value of this resistor. But it serves any resistance within the needed range. Okay. So if you need a resistance within this range, you would look for a 47 ohm resistor. Now, what does that mean if you needed a resistance within this range? Well, when you're building a circuit, you use Ohm's law with the voltage and the amperage or the current to figure out what resistances you need in different wires, also called net, also called conductors. But you can actually calculate the needed resistance, and then you can take that needed or desired resistance and go find it. Go find the resistor that's close to it, find out if that resistance that you need is in the range, and then you found the resistor that you need, because we can't make every one of the billions of resistors that are possible. That just takes up too much warehouse storage, and it would leave a lot of excess. So we use ranges of resistance on our resistors, okay? So, if you remember, if you remember the story of the yodeling goat, then you own this whole idea. So here is a yodeling goat again. Bully Brown ran over a yodeling goat because Violet's granny was gone snorkeling. That's the whole idea. So let's practice on a couple of resistors real fast. Here is a practice resistor. I'm going to actually, if you really want to test yourself, you'll need to pause this video right here, because in just a couple of seconds, I'm going to show you the answer. So pause now. Okay, now you've unpaused, and hopefully you figured out the official answer of what is the value of what is the resistance of the resistor. It turns out to be 1.2 million ohm resistor. The gold band means plus or minus 5%. Now, maybe you figured out the full range. Well done. But generally, if you know how to do the range, from then on, really all we need to do is say, add or subtract 5% to the nominal value, and you've got the full range. So when we answer these questions, we're just going to be tacking on the percentage, which happens to relate to the color band. And so let's do another one. Blue, gray, orange, gold. In case you can't read those colors, the actual words that represent them are above. You'd be surprised how many times I have to say that to students. But they're there, and I actually add the words to the tests that I give as well. Okay, pause. Okay, now that you've figured it all out, here's the answer. This is a 68,000 ohm plus or minus 5% resistor. So you've done a couple of them. Hopefully you've gotten them right. I have an assignment that I'll be giving students where they actually will do this several more times. And so I only think it's necessary to put 2 in the presentation. I think that's enough to get the idea across and to get an idea of how to do it and practice with it. But what I'd like to do now is talk about a different component for just a moment. This different component is called a capacitor, and this thing is a capacitor. The reason I'm jumping to this capacitor right now is because capacitors are read in a very similar way to resistors. Only instead of using color bands, capacitors, somebody just said, dang it, we're just going to use numbers. So the first number on this capacitor is a 4. We're just going to keep it as a 4. The second number on this capacitor is a 7. We're just going to keep that as a 7. But the third, just like a resistor, is the multiplier. And so that means we're going to tack 3 zeros on it, or we're going to multiply by 10 3 times, or we're going to move the decimal 3 places to the right. It's all pretty much the same thing. So this would be a 47,000. Wait a minute. Capacitors are not rated in ohms. In the last presentation, we talked about what capacitors are, what the units of capacitance are, and maybe you can remember that. If nobody yells it out, I'm just going to tell you it's in farads, named after Michael Faraday. Okay, so this would be a 47,000 farad. Oh, that's not true either, because capacitors are just about the smallest prefix unit gadget component that we use. If capacitors are either rated in nano, pico, is that right? Micro, nano, or pico. That's what it is. They're either generally rated in micro, nano, or pico. And when you get a microfarad capacitor, that's a big capacitor. Probably could kill an elephant with that. By the way, people can die from being capacitated, incapacitated, or something like that. In any case, be careful around capacitors, especially when they get big. When they get to be, I don't know, about the size of your thumb, you want to use caution when you're around. What do you do to make capacitors safe? You take something like a screwdriver, has a plastic or rubber or insulated handle of some kind so that you don't get shocked, and then you touch the two legs of the capacitor together, and that allows them to equalize on each side, and then they're not dangerous after that. So capacitors, the one we use in this course, are not dangerous. They're too small to be dangerous, but I just wanted you to be aware of that. Okay, so I said the capacitors are always in the micro, nano, or pico range. That would be M for micro, no, millimicro, yeah, U for micro. The mu symbol for micro, N for nano, or P for pico. This has a Z. What does Z mean? Well, Z is not a prefix. Z actually has to do with the table over here. This is a Z, and that tells us the range of capacitance. This is a negative 20% on the low end of the range to a plus 80% capacitance. So basically, it is 47,000. The prefix should be right here, and it's not. Why not? If it's not, you always assume the capacitor to be in the pico prefix. It's either going to be illustrated to be in pico, but if there's no prefix, it's always pico. Okay? So, this is going to be a 47,000 picofarad, so you would put a PF after this, with a range of Z, which is negative 20 to plus 80%. What does this 25V mean? This 25V means that if you give this thing more than 25 volts, you're going to toast it, fry it, kill it, let the smoke out. It's no longer useful. It will expire if you give it more than 25 volts. Okay, so how do you write all that stuff down? Hopefully you've already written it down because you're working ahead of me. You're trying to stay ahead of me on this. And if you get it wrong, you've actually learned more than if you just waited for me to give you the answer. So you can pause here if you want. If you have not paused or you're unpausing now, here's the answer. This is a 47,000 picofarad plus or minus, or plus, no, minus 20% or plus 80% capacitance. That's the range. Okay? So, one's not enough. Let's do another one. Oh, yeah, what am I showing you here? Sometimes this capacitor will be listed as, instead of a 47,000 picofarad, it'll be listed as a 47 nanofarad capacitor. What's that all about? Well, what they've done is they've taken the decimal point that's implied here just to the left of this P, to the right of the 0, and they've moved it 3 places to the left in the prefix on the, you remember the goat may kiss Billy, my ugly new parrot friend, from the last presentation? Well, that's what they're doing. They're actually saying that is the equivalent. If you just move the decimal 3 places to the left, it's the same thing as nanofarads. There's one more. We can move the decimal 3 places to the left again, and we can get microfarads. Now, why am I telling you this? Because final exams tend to give one of these 3 as the correct answer instead of just the picofarad, which is the one you would derive. So it could be any of these 3. You just need to realize that we're just moving the decimal to the left from pico, which is the smallest, up to nano or to micro. Okay? So here's another one to play with. See if you can figure out the total capacitance of this capacitor. Just giving you a little time to think about it. You might want to pause now. Okay, perhaps you've unpaused by now. I'm going to show you the answer. The answer is, this may astound you, 470 microfarads. Now, how did we know it was plus or minus 20? The 470 microfarads is just given. Well, some people can actually read the capacitors, and there's enough space to put on them. 470 microfarads is just given. That's nice, convenient, it's useful. But where did this plus or minus 20% come from? Well, if you look on the chart over here, if there's an M or none of these other letters, it's just plus or minus 20%. So that's where that came from. Of course, the pardon me, the 35 volts. The 35 volts simply means you're going to kill it. You're going to toast it. It will expire if you give this thing more than 35 volts. One more thing I should mention about this is that this particular capacitor is polarized. That means you need to hook it up in the right direction. If you put it in backwards, it's not going to work right. I will be talking about that a little more later on, but so one of these needs to be hooked up to ground, and one of these legs needs to be hooked up to ground, and the other one needs to be hooked up to power. Well, if it's a polarized capacitor, they're not always polarized, but if it's a polarized capacitor, you're going to find this stripe on the side, and this stripe is even more convenient because it's got a little negative side, and that means this is the ground side. But if it's not got those little minus signs there, it's still got the stripe, it still means that this side is what you connect to the ground, which means the opposite side is the side that you would connect to power, and then you will have it hooked up correctly. Also, what you need to know about this is that we might be moving the decimal around for the official correct answers on the test or other places. So it could be 0.470 nanofarads plus or minus 20%, or it could be 0.000470 picofarads plus or minus 20%. Okay, so here's another one. Going to give you a few moments to see if you can figure this one out. Work ahead of me. See if you can figure this one out before I give you the answer. Pause the video now. Okay, if you unpause the video, you've probably figured it out and you know what the correct answer is. This happens to be, if you've done it right, a 220,000 picofarad capacitor with a range of plus or minus 10%. The K does not stand for kilo. The K stands for the K code, which is plus or minus 10%. The prefix is not kilo, it's still pico. So hopefully you didn't mess that up. Okay, so again, the 100V means that if you're going to toast this thing, if you give it more than 100 volts, and the M, I don't know exactly which company that is. It might be Motorola. I'd have to look that up, but that's basically just the logo of the company that made it on there too. So that's what that means. That's the capacitor. Of course, we can move the decimal around, change the prefix on this. So if you said 220,000 picofarads plus or minus 10%, you were right, but you're also right if you realized that this is a 220 nanofarad plus or minus 10% capacitor, or this could also be a 0.220 microfarad plus or minus 10% range capacitor. Let's try another one. What's that thing? Click pause. I'll get back to you in a minute. Okay, you probably clicked unpause now, because now you can hear what I'm saying. And what is this thing? Well, it's another easy one. It's one where the actual value has been actually printed. Isn't it nice that we don't have to decode color bands on these things? So this is a 0.1 microfarad plus or minus 20% capacitor, which can be toasted if you give it more than 50 volts. And you can also see it's a polarized capacitor, so this leg over here is what you connect to the negative side, and this leg over here is what you connect to the positive side. And of course, we can move the decimal around. If it's in microfarads, that's going to be the same thing as 100 nanofarads, because we move the decimal 3 places to the right this time. And it could also be a 100,000 picofarad capacitor. Here's another one. I joke with my students. I say, this is not an ibuprofen. Don't eat it. And then they always pretend like they eat it. But this is another capacitor. Notice that it is not polarized. It doesn't matter which direction you plug the thing in. Notice it's got 2 lines underneath, because sometimes if you flip this over the other direction, it could look like it's a 501 capacitor. And so you need to have the right, read it in the right direction. Okay, I'm going to pause for just a second, let you figure this out, then we'll come back with the answers. Okay, you've unpaused. We got the 1, we got the 0, right? So we keep the 1, the 0. This is a 2, it's the multiplier band, and if we're going to write down a 1 and a 0, we're going to put 2 zeros after that, and there's no prefix on it, so it's going to be a picofarad, and there's no code on it either, so it's plus or minus 20%, right? 1,000 picofarad plus or minus 20%. But that could also, if we move the decimal 3 places to the left into the nano range, it's a 1 nanofarad plus or minus 20%. We could also move it into the micro range, which would make it a 0.001 microfarad plus or minus 20% capacitor. What have we learned? We've learned how to read the color bands on resistors. We've learned which direction to hold the resistors. Make sure the metallic band is the band on the right when you read those things. We've learned how to read them, and we use that idea also to figure out how to read capacitance of capacitors. So that's what we've done. My students would now be ready for a worksheet where they do several of these, as well as figure out several resistor codes based on the color bands as well. Thank you for listening to my second video. I've actually got 2 of them now. Come back later. We will have a 3rd, 4th, and 5th. Probably I got a lot of these presentations. I'm guessing about 50 of them. So come back soon and learn some more.